Just click up here. Okay. Right. Okay. Well, it's a great pleasure to be here. Thank you very much for inviting me. I should add that I've been ill lately, and so when people come up and introduce themselves, I don't shake hands. And that's not because I'm asocial, it's because I don't want to take a chance on infecting you or your children. I don't think I'm contagious anymore, but please bear with me. So yes, I've done a variety of things, and because this talk is we're talking here mainly about formal methods in this lecture program. I'm talking about my theorem prover. The work is joint with Matt Kaufman, but it's also joint with Bob Boyer, because as you'll see, for many, many years I've been working on this project. In fact, for 40 years. I started this project when I was doing my graduate work at the University of Edinburgh in 1970. And so what you're going to see is not a normal research talk, but more like a recap of 40 years of progress in this area. And Victor's slide of the impossible object is a very appropriate slide for mechanical theorem proving, because at first it just doesn't seem very practical. And I hope to convince you otherwise, although there are some real difficulties. So I'm going to talk about the system whose web page I've shown you here, and it's called ACL2, and it stands for a computational logic for applicative common Lisp. ACL. Common Lisp is an ANSI standard programming language. We have adopted a subset of it that's purely functional or applicative, and then we've axiomatized it in a first order logic and written down conventional rules of inference like substitution of equals for equals and modus ponens, and have created a logic for Common Lisp, for the applicative or functional subset of Common Lisp. ACL2 is unlike other theorem provers like Isabelle and Hull and Koch and NuPerl, because it's basically fully integrated into a computational framework, and that will become very clear in my talk. And this fact that we focus on computation makes the theorem prover somewhat more limited than the systems I just mentioned. This project is ongoing and long-lived. Boyer and I started it when we met in 1971 in Edinburgh, and we developed there a theorem prover called the Pure Lisp Theorem Prover, and that morphed eventually into a theorem prover called InQthum, and then finally into ACL2. And then after about 20 years, Bob decided he wanted to do something besides theorem proving, and he'd always been interested in philosophy, so he changed from the computer science department to the philosophy department and taught Plato and Socrates for the last 20 years of his career. He retired recently. Meanwhile, I picked up a different partner, Matt Kaufman, and he and I continued the development of the system, and that continues today. The kinds of theorems we were proving in the 70s were simple list processing theorems, and then in the 80s we started proving what I call academic computer science and math theorems, and then in the 90s we started moving into commercial applications. And this is, if I had that little object that Victor showed, you could kind of lay it down here, and it looks impossible when you're thinking about the examples I show you here, and it's actually being done when I show you the examples here. So let me give you a simple example of something we did in the 70s. And again, I'm using Lisp as a logic, but I'll explain every piece of Lisp you see. So this is a formula that says that AP, which I will pronounce append, AP is an associative function. And this is the Lisp expression of it. Think of all formulas as universally quantified on the far outside, and I use Lisp notation instead of infix, but it should be familiar enough. And it just says that this function is associative. The function has a definition in Lisp. This is a recursive definition. I'll paraphrase it. Oops, sorry. I hit the wrong button. To append x and y, if x is empty, return y. Otherwise, make a new ordered pair whose first component is the first component of x, and whose remaining components are obtained recursively by appending the cutter of x to y. Okay, so that's a recursive description of how to concatenate or append two lists. So if I have the list 1, 2, 3, which is really a nest of ordered pairs with 1 as the first component and the list 2, 3 as the right-hand component of the first pair, and I append it to 4, 5, 6, I get that list. Now from this definition, it's easy to derive two trivial corollaries. One says if x is empty, then append xy is y. And the other says if x is not empty, then append xy is the cons of the car of x onto the append of the cutter of x and y. And you'll see me use these later. And so then we contemplate proving a formula like this. We want to prove this for all A, B, and C, and the only thing that we can do, since we don't know how long A, B, or C is to try mathematical induction. One of the highlights of our theorem prover is that it does inductions automatically most of the time. So it does an analysis of the recursions involved in this theorem and decides that it will induct on A. And I will show you a little more about that later. But it starts by saying I'll try a proof by induction on A. And roughly speaking, it's because this append is decomposing that A, and this append is decomposing that A. But this append is decomposing B, and it had to think of a reason for why not to induct on B. And the reason it didn't induct on B is that B is being held fixed by that append, and if you try an induction, you'll find out that this term will prevent an induction on B from working. So we're going to do a proof by induction on A. The base case is if A is empty, and we want to prove this formula under the hypothesis A is empty. And now, given the first corollary I showed you, if A is empty, append AB is equal to B. So I'll do that substitution of equals for equals. And now I'm going to focus on this append, because again, it's about an append of A that I know something about. And so again, because A is empty, this append is equal to its second argument. So I get that. And now, of course, I have an equality of two identical terms, and there's an axiom that says x is equal to x, so that reduces to true. So that's the base case. Now the induction step starts by saying, suppose A is not empty. I wish to prove this conclusion, but I get an induction hypothesis. And the induction hypothesis is an instance of the formula I'm proving, but with A replaced by something smaller. And the smaller thing I choose is the cutter of A, the right-hand component of the pair that A is when A is not empty. So now, given this hypothesis and this condition, I wish to prove this formula. Again, I focus on that inner append. And because A is not empty, and using the second corollary I showed you, that I can replace that append by a cons. Now I focus on this append, and the first argument to this append is not empty because it's a cons. So I can use the corollary again and get this. Then I focus on this append, and because A is not empty, I use the corollary and get this. And now I'm trying to prove that one ordered pair is equal to another ordered pair, but the left-hand components of each pair are identical. And so there's an axiom that says two pairs are equal if and only if the left components and the right components are the same. So I can reduce this equality to that equality. And now I observe that that's my induction hypothesis. So by induction, that's true. So I'm finished my induction case. So that's a typical proof that we were doing in the 70s. Now, I'm sorry, this is a walk through Cornwall that we did last year.
I guess you also know that sufficiently many queries will result in a null list.
Yes. Well, that's actually not quite true. Sufficiently many cutters will result in nil. And the nil is considered the empty list. It's not a pair. And the cutter of nil in common Lisp is nil. And so, right. So on this screen, I have ACL2 running in an Emacs shell buffer. And I can type things like cons1 onto cons2 onto cons3 onto nil and get back the list 1, 2, 3. And I can take the car of that list and get 1, and I can take the cutter of that list and get 2. And I have in the background a little script that allows me to type in a formula without making any mistakes. And so here is the definition of append that I showed you a moment ago. And what this command does is it adds that as an axiom. And when you add a new axiom to a logic, if the axiom purports to define a function, the logic requires that you prove there exists a function that satisfies this recursive equation, which we do by exhibiting a measure of the arguments that decreases in a well-founded way. I'm not going to talk about that, but what ACL2 just did was verify the termination of this recursive function. Now, I can run it as I showed you. So I can type any two lists and append them, like A, B, C, D, E, F, and I get A, B, C, D, E, F. Case insensitive here. And then I can type a challenge. I can say, prove the theorem that append is associative. The name is just used so that it can refer to this theorem in the future should it decide to use it. But it can't use it unless it can prove it. I'll talk about that in a moment. So I'll hit return, and you'll see it print out a proof. Okay, well, that was sort of fast. I'm going to go back to where I was. And it says, perhaps we can prove it by induction. It decides it will induct according to the scheme suggested by append AB. Here's the induction hypothesis, the induction argument. It says if A is not empty and the formula holds for the cutter of A, then prove that it holds for A. And the base case is if A is empty, prove the formula. And it's justified by the same argument used to admit append. It generated a bunch of subgoals which it didn't display, but each simplified to true as I showed you earlier. And so it finished, and now it's stored into its database the associativity of this function. So I just adjusted the output. So here is a Lisp function that inserts the object E into a list, and it uses lexicographic ordering, which is a total order on ACL2 objects, so as to keep the list X ordered. So for example, if X is empty, then you just add E to the front of X. If E is less than or equal to the first thing in X, you add E to the front. Otherwise, you add the first thing in X to the result of inserting E into the rest. So that function terminates, and if I insert 3 into the list 1, 2, 3, 4, it goes after the 2 and before the 4. And if I insert Bravo into the list Alpha Charlie Dog, it goes after the Alpha and before the Charlie. Now I can define insertion sort, which says if X is empty, return X. Otherwise, insert the first element into the sort of the rest. That function terminates. I can try sorting a list of arbitrary objects, and I get lists that look ordered. So now my challenge is, let's prove this little piece of software correct. And to do that, I have to specify it. And that means I have to define the notion of what it is to be an ordered list. So here is the definition of ordered. It says X is ordered. If X is empty, then it's ordered. If the rest of X is empty, then it only has one thing in it, so it's ordered. And if X has 2 or more things in it, then the first must be less than or equal to the second, and the rest of the list must be ordered. So that's a recursive definition of ordered. And now I can test it. For example, that list is ordered, and this list isn't because this 3 is out of place. So I get nil, which is false in Lisp. And so then I can challenge the theorem prover to prove that I sort of X always returns an ordered list. And it proved it, that there's the QED. Just recapping the proof really quickly, it did an induction, it did some simplification, it identified a sub-goal, which it worked on a while and then pushed for induction, and it proved that sub-goal by, notice here it generalized that sub-goal. It decided it should try to prove that if IT is ordered, then inserting X1 into IT is ordered. So this is the specification for insert, which I didn't tell it, but it derived as a way to prove that ordered produces ordered lists. And it proved this by a second induction, and that completed the proof. So I've just proved that isort produces an ordered list. So many programmers would think, okay, I've proved that isort is correct. Well, here's an even faster way to sort. I'll call it fast sort. It will return it. It will ignore its argument and return 1, 2, 3, 4. Okay? So now, for example, if I sort that list, I get 1, 2, 3, 4. If I sort this list, I get 1, 2, 3, 4. Okay, this is a really killer sort routine. Works in constant time. Furthermore, of course, that gives away the secret. But interestingly, or not, I can prove that fast sort always returns an ordered list. That is, I can prove the same thing about fast sort that I proved about insertion sort. Namely, that it returns an ordered list. It's just a trivial theorem. And so there's something wrong here. And of course the problem is that there's more to the specification of this piece of software than ordered. And the key is that a sort routine is supposed to return a permutation of its input. So I have to define permutation, and here I reach out and grab a book of other lemmas proved, and this is a book about perm. And here's the definition of perm. It basically says X and Y are perms if for every element of X I can find an identical element of Y, and if I delete them both, the results are still perms of each other. And so that's the recursive definition of perm. So, for example, these two lists are perms of each other, and these two lists are not, because there's a 4 in one and not in the other. So here's my good definition of sort. I can prove that isort produces a permutation of its argument. Okay, that was good. And so now I might try to prove that fast sort produces a permutation of its argument. And that failed. And so the key is it doesn't say QED at the end, it says failed at the end. And it printed some checkpoints. One of the checkpoints it would need to prove in order to prove that fast sort was correct was to prove that 1 is a member of every list, and we can't prove that. So that's the end of the first demo, and now I'll go back to here. So the way ACL2 works is, the way the user uses ACL2 is kind of exploits the structures of proofs. A proof is a tree with axioms at the roots and a theorem at the bottom, and these rules of inference transform known truths into other truths. And so, for example, this might be substitution of equals for equals, and you give it a truth and it yields another truth. And some lemmas in the intermediate part of the tree are key in the sense that they're somehow important. And the observation is, if your challenge is to find a proof of this formula, you need to, explore the proof trees back to the axioms. And if you have already proved this formula, then you have to explore less. And that's the main idea, that if when I give the theorem prover this formula, it looks in its database and it finds this formula, then it can perhaps find a proof of this one by exploring just for this simpler subtree. So the way the theorem prover looks to the user is the user types definitions and conjectures to it. The theorem prover prints out proofs and draws on a database of previously proved facts. And anytime something is proved, it's added to the database. So if I have a key lemma, I challenge the theorem prover with it. It tries to prove it, and if it does, it stores it in the database. And then when I present the main theorem to it, it finds that in the database. The user cannot just reach over and put something in the database. So that means the theorem prover is responsible for soundness, and the user is responsible for strategy by proving the key lemmas first. At a deeper level, the theorem prover looks like this. The user puts a formula into a pool. A procedure called simplification draws one formula out of the pool and replaces it by a conjunction of formulas that are equivalent. And if the simplifier can do that, it just keeps doing it until it draws a formula that it can no longer simplify. And by the way, it may replace the formula by a conjunction of 0 formulas, that is true, so that it just proved the formula it drew out. But if the simplifier finds a formula it can't do anything to, heuristically, it gives it to another procedure which tries a different technique, and that puts formulas in the pool or passes it on. And we try a variety of proof techniques until finally we get to induction. And by the time we get to induction, we've tried some rather risky techniques like generalization. The original formula is proved when the pool is empty. The simplifier contains 40 years of work. It contains a lot of decision procedures, many complicated rewrite heuristics. It allows you to define your own theorem prover in Lisp and prove the theorem prover is correct, and then use that theorem prover as a component of this one, which is actually done quite frequently by our users, and many other techniques. The key to our success is largely the careful integration of these techniques. So now, moving from theorems like append and insert, let's go to the 80s. And the first interesting theorem we proved in the 80s was the undecidability of the halting problem. So we formalized pure Lisp in this language and proved that the halting problem for it was undecidable. We also proved that pure Lisp was Turing complete, so that it was really the halting problem as we know it. And that took 18 lemmas. We also proved the invertibility of RSA encryption, and that took about 180 lemmas. And there what we had to do was start to teach the theorem prover the beginnings of elementary number theory through the prime factorization theorem and a few facts. Then a student came along and proved Gauss's law of quadratic reciprocity, developing still more number theory. And another student came along and proved Gödel's first incompleteness theorem, which he had to prove about 1,700 lemmas for, and it was a formalization of Gödel's 1931 paper, in which you introduce the notion of tautologies and proof checkers and formulas encoded as objects in the logic and Gödel numbering and so on. On that CS side, we proved what is called the computational logic verified stack, and that was a software stack that started with a gate level machine coded machine, a microprocessor, an assembler, linker, and loader that transformed assembly code into binary images. We verified that the assembler preserved the semantics of the assembly language while executing on the gate level machine. Then we verified some compilers for pure Lisp and for a subset of Pascal. And we verified a simple operating system. And this was done between 1988 and 1992. And all that was put together, and we actually fabricated the microprocessor. It was called the 9001, so that we had a net list description of a physical object. Notice, one doesn't prove theorems about physical objects. One doesn't prove it takes a cannonball this long to fall from the Tower of Pisa. Instead, one proves that according to some model of mechanics, it will take that long, and you prove the theorem about a model. And it's an engineering exercise as to whether this formal artifact, a net list, is realized by that physical object. But once you get the formal model, then you can build on top of it. And so from the formal net list description language, we went up through machine code, assembly code, and to this subset of Pascal. And then you could write a procedure in that, compile it, assemble it, link it, and load it, get a binary image, and know that the execution of this code was correct on that machine. That was called the short stack. And then we moved into the 90s. And by this time, we were interested in trying this commercially. And in 1994, Intel released the first Pentium. And a few months later, it was shown to not divide correctly. In particular, in the New York Times in November of '94, there was the headline, "Circuit flaw causes Pentium chip to miscalculate. Intel admits." It was known sometime before Intel admitted it. And then a few months later, Intel wrote off $475 million so they could buy back all the Pentiums they had sold and replace them with Pentiums that did know how to do floating point division. Now, simultaneously with this event at Intel, Intel's main competitor, AMD, Advanced Micro Devices, was about to release their version of a high-end fast microprocessor, which at that time was the K5. And AMD was terrified that they might have a mistake in their floating point division. But let me back up. What is floating point division supposed to do? This is the IEEE standard, and it says that elementary operations like division are to be performed as though you did it to infinite precision and then rounded the result to the indicated precision. And I'll be a little more clear about that later. But AMD had an algorithm that they had more or less invented because they had made another mistake in the production of the K5 and had allocated insufficient area. Think of a chip as a piece of real estate, and they give a certain amount of real estate to, say, the floating point unit, and another to the ALU, and another to the memory management unit, and so on. And it turns out that they gave insufficient space to one of these other teams. And 9 months before this machine was due to hit market, they realized they needed to take space away from the floating point unit. So they went to the floating point team and said, we're going to reduce your space by 30%. Figure it out. And so what the floating point team did was they threw out floating point division and floating point square root and the transcendentals and implemented them in microcode using the hardware that was left that had been tested for 18 months. Now, unbeknownst to AMD, they made this decision at the very time that Intel was discovering they had gotten floating point division wrong. So here AMD was committing to going with an untested divider in the same market space that Intel had just had a disaster in. And when I say untested, you'll see what I mean in a moment. They had months to test it, but that's hardly enough. So they made up an algorithm, and I'll show you a little bit about it, but basically it was a 32-step, 32-cycle algorithm written in microcode, and this is the pseudocode for it. And for example, one line, this line, let me stop that so we're not seeing pictures of Cornwall. The line 5 says that you take the floating point number in this variable or register SD1, multiply it by the floating point number in D sub r. Think of that as an infinitely precise rational multiplication. Round it away from 0 so that the exponent fits in 17 bits and the significand fits in 32 bits. And that's a floating point number now. So this and this is just a floating point multiply with that precision. And take that rounded floating point number and put it in this variable. And it's just a straight line code like that. Now the way the algorithm actually works is, for example, to divide 12 into 430. The first thing it does is it computes an approximate to the reciprocal of 12. And I'll show you how it does that in a moment. The actual reciprocal of 12 is 0.08333 forever. But because we're working in floating point, we only have an approximation to that. And let's suppose the approximation were 0.083. That turns out to be what's in variable SD2. And now multiply SD2 times 12. The actual answer is this. But you can't represent that precisely in floating point, so round it. Let's say we get 2 digits. So it's 36. And that's the first partial quotient, Q0. So put that here, and now do another multiplication of 36 times 12. You get 432. Do a subtraction, you get minus 2. And what I've just shown is that 12 goes into 430, 36 times with a remainder of minus 2. And now repeat that. And repeat it 4 times. And then sum up these partial quotients using floating point arithmetic starting with those two, and then add that one in, and then add that one in, and then truncate it to the precision you wanted the answer. And AMD said that's the right answer, that's the floating point answer. And the question is, was it? And by the way, at no point did you see me do anything besides multiplication and subtraction here, which was on the part of the unit that had been tested. Now, to do the reciprocal, they used a Newton-Raphson approximation. So you take this, I won't go into Newton-Raphson. This is an iterative equation. You iterate it a couple of times and you get an approximate to the reciprocal. So you have to give me an initial guess, and one iteration gets me closer to the reciprocal, and another iteration gets me closer still, and AMD decided 2 iterations was enough, assuming that their initial guess was wildly appropriate. And they have a read-only memory that's got initial approximations for the reciprocals of a bunch of numbers. And so you take the divisor, you look up its top 8 bits in this table, and you get an approximate to the reciprocal, which you then feed into Newton-Raphson 2 iterations, and then you do that multiplication, subtraction, long division-like algorithm, and then a sum. And that is the algorithm AMD used. And so the question was, if AMD builds it, will it work? A bug could cost AMD hundreds of millions of dollars, and to test all possible combinations on the fastest machine today would take about 10 to the 27 years. So this is not the kind of thing you can test in 9 months. And so they decided to try to prove it. And that's what got us involved. And so my partner and I, Matt Kaufman, made a model of the microcode in Lisp. And every line of this corresponds to a line in the pseudocode. And then we wrote this theorem, which it says that if P is a floating point number in this format, 15 bits of exponent and 64 bits of precision. That's a normal double precision floating point. Inside they use 17 bits of exponent, but outside they use 15. And D is also such a floating point number, and D is not 0, and mode is a rounding mode in the IEEE standard. Then the output of the algorithm, which is the model of the microcode, is the infinitely precise P divided by D, rounded according to the IEEE method, according to mode. And Matt Kaufman and I proved that theorem before the K5 was fabricated. We signed the non-disclosure agreement 12 weeks before the K5 was fabricated, and we proved this theorem in 9 weeks. And in the process, we had to prove 1,200 lemmas about IEEE floating point operations. By the time 1997 had arrived, AMD was doing this in-house with some people that had been trained by us. In fact, the lead was the person who did Gauss's quadratic reciprocity proof. And by 1997, when the Athlon was produced, all of the elementary floating point on the Athlon was verified to be IEEE compliant, and the proofs were checked with ACL2 and mechanically. And that happens routinely. Every microprocessor AMD builds today has its floating point unit verified by ACL2. The same thing is true of Cintar, which produces the VIA microprocessors. The same thing is true of Intel, except they don't use ACL2. They use a theorem prover that they produce in-house. So between 1994 and today, we've seen a sea change in the way microprocessors, or at least floating point units, are built, with theorem proving being the method they use to certify correctness. This has also reduced the amount of time AMD spends testing, because they have now libraries, what we call books in ACL2, books of thousands and thousands of theorems about AMD components and notions like sticky rounding. And when they build a new processor, they often use some algorithms they've used before, but maybe represented in a new way. And they can prove them correct by appealing to previously proved lemmas and a few new facts, which they prove. So this is, as I said, a sea change. Now I should note that even though AMD regards this as hardware verification, it's really software verification, because what we did was prove a theorem about pure Lisp. Every theorem we prove is a theorem about Lisp, because Lisp is the logic and the programming language. And so, in a certain sense, there's really no difference between hardware verification and software verification. The difference is sort of, if there is a difference, it's that generally hardware verification is finite state. But in this proof, we did not exploit the finite stateness of the exercise. It is finite state. There's only a finite number of floating point, of double precision floating point numbers. And there's only a finite number of IEEE rounding modes. But if you try to prove the theorem by state exploration, you won't succeed. So think, even though you'll see me talk about hardware verification, a lot of the stuff we do is, everything we do can be considered software. So going on in the 90s, I've talked about the first one, the K5 and AMD's Athlon. We used a model of the Motorola 68020 and verified the Berkeley C string library by compiling the C string library with GCC and then verifying the binary with respect to our model of the 68020. We discovered bugs along the way. By the way, AMD discovered 4 bugs in the Athlon that had survived all the testing. And those bugs were fixed before the Athlon was fabbed. Rockwell-Collins, which produces avionics microprocessors, Rockwell-Collins uses ACL2 to verify a variety of things, including this thing, which is a crypto processor that has been certified to be safe for what's called multi-level security. IBM also used it to verify the floating point on the Power 4, at least some of the floating point. The Rockwell proof obtained what's called EAL level 7 of the common criteria status, and it was certified by the American National Security Agency as being a device suitable for multi-level security on the basis of the proofs done with ACL2. And that's changing the way they do this kind of certification. So now what they often do is present the certifiers with a model of the device and a theorem about it. And then the problem is to convince the certifiers that the model accurately describes the device. Rockwell also proved that the Green Hills operating system had a certain separation property, and Centaur, which is otherwise known as VIA, verified their media unit. And the media unit of the Centaur microprocessor, it's an x86, is very complicated. It's 33,000 lines of Verilog just to do floating point addition, so it gives you a sense of the size. In any case, the media unit of this microprocessor has been verified with ACL2. And we also have a model of the Java virtual machine, and I'll show you that. Oh, here's Cornwall again. So we modeled the JVM in ACL2, and you should just think of a Lisp interpreter for JVM bytecode. And it executes most of the J to ME instructions. It was created by a graduate student who's now working at AMD on floating point verification. And it supports all the data types of the JVM except for floating points. And I just told Hang Bing not to put floating points in because we had a lot of experience with floating point, and he wasn't going to learn much about floating point by recapitulating that. And we were actually hired to do this by Sun in order to verify properties of the class loader. They wanted to verify that class loading and class initialization maintained certain invariants that were critical to security. So we built a tool chain that allows you to take a Java file and compile it with Javac to get a class file, and then convert it to a Lisp representation of that class file and feed it to ACL2, where we could run it as you might run any model in ACL2, or prove theorems about it. And I'll show you that. By the way, the fact that ACL2 is executable is very important to our customers. Rockwell builds models of microprocessors with ACL2 and then executes them to test them before it tries to prove them. AMD ran over 100 million floating point test vectors through its ACL2 model before it tried to prove anything correct about them. So execution is very important here because it's a way to check that the model and the physical artifact are in agreement. An imperfect way, I should note. This ACL2 model of the JVM also includes the ACL2 representations of 87 of the classes in the Java API so that we can invoke those methods. And the model itself is 160 pages long, so it's quite a big Lisp system. You can do a lot in 160 pages of Lisp. So let me show you a bit about this model. I'm switching over to a package where this model is defined. Oh, before I do this, let me get in this buffer. And if I do cat_facts.java, here's a little trivial Java file that defines a static factorial method that works on ints and computes factorial recursively. And then a main method that just parses the string argument as an integer base 10, calls fact on it, and prints it out. And I can compile that and then run it, and for example I can say Java fact of 6, and it says that's 720. That's factorial of 6. I can also print out the class file for factorial. And what I want to draw your attention to is this is the Java bytecode for that fact method. It's just an assembly code for the JVM. And what I'm going to show you is an ACL2 model of this. Well, it's a model of the JVM, but inside it, as part of the state, is this code. So going back to ACL2, I'm going to print the ACL2 representation of the JVM state. Now, this state is very large. I won't try and explain it all. In fact, I'm waiting for it to type it all. It's about a megabyte of text is being scrolled into my buffer right now. But if I search down here for actually demo, here is the representation in ACL2 of the method fact. And you can see it looks just like a sort of parenthesized version of the bytecode I just showed you. And this is what's actually in the class file that the Java compiler produces, except we've turned it into an ACL2 object. So this object is just part of a state that has a representation of a heap, which is a map from addresses to objects, a representation of a class table. This is part of the class table. And a representation of a thread table, which is a list of threads, which is each thread has a call stack, and each call stack has a frame showing which method is executing now and what its local operand stack is, and so on. So formalize the JVM as a big Lisp function. So here is the definition of the semantics of the instruction IAdd. And what IAdd does, it takes an IAdd instruction and a JVM state. It lets V1 and V2 be the top and the second from top element of the stack in the currently active frame. It adds those two numbers together, fixes it to be a 32-bit int, pushes it on the result of popping two things off the stack, and advances the PC. That is the definition. That's what the Sun JVM says IAdd does. Here, for example, is the semantics of invoke virtual, and it's much longer and more complicated, but basically it involves method resolution and all kinds of other things, and involves, in fact, this method right here, call virtual method, is itself a very large piece of code that, well, call method general, and so on. This is just a very careful encoding of the JVM that was built off a C version of the JVM provided by Sun. So here is the top-level interpreter, and I've simplified it by eliminating the possibility of threads, so I call it simple run. Simple run takes a Java state S and a number n. If n is 0, it returns S. Otherwise, it steps the machine one step and decrements n and then continues to run. So this just hits S n times with a single step function. And the single step function is kind of what you'd expect. It says if the current op is, for example, let me find one, IAD. If the current op is IAD, then execute the IAD instruction. So it just does a big case analysis on all the opcodes in the JVM and calls the ACL2 model of each single stepper. So I can run this. I can say, pretend that the fact method is presented with the string 6. What do you get? And it said you get, the output stream is 720 new line. Okay? It had to load these classes in order to compute that, because those classes were not in the initial state. But you can interpret that as saying factorial of 6 is 720. So I can say, well, here's the actual factorial of 6, and it's, of course, 720. Now I can say, what happens if you present the JVM model with a string 20? And you get a negative answer. And that might be counterintuitive, and so you might go back to the actual JVM that's running on this Linux box, and I ask it Java fact of 20. And it says I'm going to return that number. That's a negative number. And if I go back here and compare that, I'll put that negative number right here. And you can see it's the same number. So my model and the JVM that I have on this machine from Sun actually produce the same number. So that's interesting. But what number is that? Well, if I take the actual mathematical factorial of 20, I get this number, which is bigger than 32 bits. And if I convert it to a 32-bit number, that is to say, if I take the low order 32 bits of it, I get that number that we saw. So here's a hypothesis. This says, if you have I won't show you this definition, but what it actually says is, S is a JVM state that's poised to invoke the factorial method on n, where n is an int. And if you run it a certain number of clock ticks, a certain number of bytecodes, you get this state, which is obtained by popping the stack, computing the actual mathematical factorial of n and converting it to 32 bits and pushing it on the stack, and then advancing the PC by 3 bytes, because that's the length of an invoke static instruction. So this is a theorem that essentially makes an invocation of factorial look like a bytecode operation, because it's got the same shape. It says advance the PC and adjust the stack. And I have to give ACL2 a hint on how to prove this, and I do that. But now you see ACL2 crunching away, and there it just proved that fact is correct. So what I've just done is prove about 160 pages of JVM model and a definition of fact obtained from the Java compiler that it actually computes factorial, at least the low order 32 bits of factorial. And I can infer from that another observation. Here's a little lemma I had to prove. But here's a nice observation, which is, let me just show you. If I go back over here and say, compute Java fact of, say, 35, I get 0. And Java fact of 40, I get 0. I'm going to get 0 almost all the time, because eventually the lower to 32 bits are all zeros, because there's that many powers of 2, products of 2 in the answer. And so here's that theorem. It actually says if S is a state poised to invoke fact on n, and n is a natural number greater than 33, then the top element of the stack after running factorial is 0. So that says that, you know, if you wanted to implement factorial as a fixed num like this, you could be almost always right by just returning 0. And we can prove that. So, just to wrap up, I'm not going to go into this because I'm kind of running over time. But there is the question, how do I know ACL2 is sound? And the obvious answer would be, well, prove that it's correct. You can't prove ACL2 correct with itself. because if you did and it said, yeah, I am correct, you wouldn't know if it was lying. However, there are ways. And so you could do something like this. Suppose you have a theorem prover, and it proves this formula phi, and suppose that you annotate this theorem prover with a proof generator, so it produces a proof pi of phi. And then suppose you have a proof checker that you checked, that you like, that you approve of, that you agree is a proof checker. Then you could call this theorem prover, and every time it produces a proof, you could check the proof with this proof checker, and if it said yes, then you would know the theorem prover was correct for that run. Now that's a good idea, but it's going to be too slow in general. But why don't you then use this theorem prover to prove itself correct? And you generate that proof. And then you check that proof with this proof checker. And if it says it's correct, then it's correct. Now, that's an impractical thing to do because the proofs get too big. This is a description of that. You use the theorem prover to prove it's correct. You generate that proof. You check that proof with this one. And you never have to generate any low-level proofs again. The trouble is these proofs are too big. And so what you end up doing is building a stack of theorem provers. A primitive proof checker at the bottom that you just trust because it looks just like Gödel's proof checker in his 1931 paper, say. And then you derive a few rules of inference and you prove another theorem prover that automatically does propositional reasoning. And now once you verify that that's correct with respect to this, you can trust this one. And now you verify more rules, and you just work your way up and eventually introduce high-level things like case splitting and conditional rewriting and induction, and you finally get, in our case, 11 a stack 11 deep of verified theorem provers, and this one has been verified by that one, but that one was verified by this one, and so on down to there. And then you can put it all together and derive that this one, when this one says it's a theorem, there exists a proof that this one will check, even though I cannot create that proof because it's too big. Now that was not done for our theorem prover, but it was done for a simplified version of our theorem prover by a graduate student, Jared Davis. And his system is called Malauer, and if you look at it, you can find that on his web page. So why are we succeeding? One answer is our mathematical logic is an executable programming language. So our customers can execute their models to see if they work. And furthermore, the language is supported by many platforms. ACL2 runs under any Common Lisp, and we test it on 6 or 8 different Common Lisp on a variety of platforms, Linux and Windows and others, before we release it. And we don't have to do the heavy lifting of maintaining a compiler and everything. Secondly, we've invested 40 years in supporting efficient execution and integrating many proof techniques and engineering it to deal with industrial scale formulas. And over that 40 years, we've also developed a lot of books that our customers use. I say customers, we don't charge anything. It's available for free on the net. I'll put back the home page in case you want to get it. A third reason is we choose to use ACL2 on problems that it's appropriate for. And it's not appropriate for everything. There's no quantifiers in ACL2. We don't have real numbers in ACL2 because we only have the rationals, because that's what Common Lisp provides. We don't provide the floating points, but you can model floating points with rationals, which is what we can do. We use ACL2 to model bit and cycle accurate microprocessors and other computational artifacts. I would not try to prove theorems about set theory with ACL2. It's just not appropriate. ACL2 is a computational logic designed for proving things about discrete, inductively constructed objects. And finally, the reason industry uses it is kind of cynical, but they don't have another choice. If it takes 10 to the 27 years to test the things they're building, what can they do? I mean, this is fast by comparison. Basically, industry is building artifacts that are so complicated that people don't always understand them. And only by interacting with a tool like this can you come to feel confident that you understand. So our hypothesis is that the high cost of formal methods is a historical anomaly because we happen to be where we are in the history of computer science. We've got a huge amount of folklore, some of it formalized, much of it not, and little of it formalized in mechanically checked mathematical systems. But every year that goes by, there's a larger repository of mechanically checked results. And it begins to be easier and easier to prove new, say, designs correct by referring to past proofs. And we believe that as time goes by, the cost of doing formal proofs of hardware designs and ultimately software, when we replicate that database of commonly used ideas, will decrease. And so we believe that mechanized formal methods will not only decrease the time to market, but increase reliability, which is why AMD and Intel and the other companies are using this. It already is doing that compared to testing. And we're slowly branching out into software, but at low-level software like the JVM, and that's because there's reluctance to invest in bulletproof proofs about software if it's assuming the correctness of a compiler and an operating system and the underlying hardware. And so I think that, realistically speaking, software verification won't take off until Intel produces a specification of the x86 that Intel lives with and says, okay, this is what this machine does, and you can take it to the bank. And then somebody will produce an assembler, and they will be challenged to prove that that assembler preserves the semantics of the assembly language they advertise, and then a compiler, and so on. And that's what the short stack did, and that's what will ultimately happen for actual microprocessors, but it takes a long time, and I'm talking about decades here. I mean, it took industry decades to start to share netlist description languages, because they each treated their own netlist description language as a proprietary product. And they pretended that their designers never talked to designers in other companies, much less changed jobs. But designers moved around a lot, and pretty soon everybody knew Verilog and HDL and this, that, and the other, and suddenly formal models, or at least accurate descriptions of those things, were promulgated. And the same thing has happened with floating point. And as standards increase and multiply and are adopted, then starting at the bottom we'll see formal methods come up behind it, because these artifacts are very complicated. So in conclusion, mechanized reasoning is already changing how we work, how things are designed, and the notion that something is too complicated to prove is exactly the reason you should try to prove it. And here are some references. There's a book, if you want to get it, and you can find it on the web. And our web page is there, and has about 10 megabytes of documentation and other stuff on it. So, and the sources for the code. So I'll stop. Thank you very much. I'm happy to take questions if we have time. You can direct.
Okay, I have two questions. The first one, you said in the beginning, you said, okay, I go and want to prove a certain theorem, and then it's essential that I have a sort of halfway between a lemma.
Yes.
And then you were giving your examples, and you had thousands of lemmas.
Yes.
And so what would you do? What happens practically? You take each one of those and try to prove, and I mean, in your database.
I see. There are really two questions. One is, how does the theorem prover find the lemmas that are already in the database that are relevant? And the other is, how did they get into the database in the first place? Because the real question is, how does the user respond when a proof fails? I mean, that's the most important question. But to answer the first one, the lemmas are indexed in a variety of ways, and when the user proves a new theorem, he or she attaches to it a note that can give pragmatic advice on the situation in which, like, don't use this unless you can find a value for this variable with this property and that kind of thing. So there's pragmatic notes that you can attach, and you can also give hints, like I did for the JVM proof. So you can give a hint that says use this lemma, for example, or don't use any lemmas but the ones in this collection of lemmas, and things like that. We try to build the databases. Good users try to construct their, like AMD, constructs their floating point database so that the kinds of proofs they expect to be automatic are automatic. But they engineer those rules carefully and store them in ways so that the system finds them. But if you try to prove something that's unlike the kinds of the style that AMD uses to express floating point theorems, even though mathematically it might be the same, the method might not find it because of the way things have been indexed. On the other topic, when you try to make ACL2 prove a formula that it can't prove, when it fails, it prints what are called checkpoints, which are formulas that it sort of is inviting the user to consider proving. Or so you look at these checkpoints and you say, oh, there's a subterm. Like I might see inside a checkpoint a subterm like f of x and 0, and I might know that 0 is an identity for f. So I think to myself, I'll prove that f of x and 0 is x. And I prove that as a lemma, and that checkpoint now goes away because that term is simplified. And so you look at the checkpoints for facts that you know that the theorem prover doesn't know, and you state those facts as lemmas and try to prove them. And that's how you evolve these big databases. The proof of floating point division had 1,200 lemmas in it, but really the proof itself at the top level has 6 or 7 lemmas. And Matt Kaufman and I, on the blackboard, produced a high-level proof of the floating point, and then I said, okay, I'll prove these 3 lemmas, and Matt said he'd prove those 3 lemmas, and then we'd put our results together. And then I just went away and proved my 3, and he went away and proved his, and every day we would come back and say, hey, I need to prove this sub lemma, and Matt would say, oh, I proved that yesterday, here it is. And pretty soon we built up this big tree of lemmas. And
if you allow the second question, you said about the hardware verification, basically you have a software model and that's the one you verify.
Yes.
But then, and the other would then be engineering a question,
yes,
whether the hardware actually corresponds to your software model.
Yes.
Or vice versa. But that might take 10 to the 27 years.
Yes, the question, it's really an engineering question. Does a mathematical model account for all the things that I think might go wrong? I mean, you know, we build models of things mathematically, and we intentionally ignore certain things like friction or the weight of the object or color or something, but we ignore aspects of the reality when we make our models. And then there are some things we can deduce about the models that you sort of have no physical significance, and some things we can't. And that is a deep question. When does a mathematical formula or a set of mathematical axioms correspond to predict the behavior of an actual artifact? And that's basically an engineering question. And I can't offer. The way we approach that is that we try to make our models line for line analogous to the engineers see the Verilog or the netlist as the actual physical artifact. It's not, but if I can produce a model that is thank you. If I can produce a model that is line for line accurate with what the engineer thinks of as his actual model, then the question then becomes, why does the engineer trust the layout and the fab part? And so that's what we try to do. And that's what Rockwell did when they verified a C kernel for a separation for an operating system, and then had it checked by NSA, as it was line for line. For every line in the C, there was a line in the ACL2, and they had to establish a certain kind of correspondence between the C and the ACL2 implementation or model of it, and then just read the lines. I should have turned this off before I started. Yes, any more questions?
You said you verify compilers. What does it mean? If I type anything that is accepted without errors by the compiler, and I compile that...
Well, the compiler has a specification. I mean, typically the compiler specification starts with the semantics for the high-level programming language. And then you prove that if you have an input for the compiler that satisfies some syntactic characterization, and you execute that program to, say, to termination with the high-level programming language semantics, you get the same result as if you take that program and compile it and get a low-level machine, execute the low-level state to termination, and then you can relate these two states, typically, for example, by projecting this one up so that all you look at are the answers. And so you get commuting diagrams or bisimulations that show that the two machines correspond in some way at execution. And that's a typical... and for example, in the compiler proofs that we did, you also have to characterize the resources used, because the lower level machine only has a finite stack, only has finite memory. And so the upper level machine in principle has infinite memory. But you might say, for example, that the two final states correspond provided the low level state doesn't go into an error. That you characterize error states at the low level, and you say that either an error is signaled or the final state is what the high level machine would predict. But it's a theorem like that is the correctness of a compiler, and it typically tells you, in our versions, it also tells you, if you noticed when I proved the JVM implementation of factorial correct, I actually proved that if you had a state poised to execute factorial and you executed it a certain number of clock ticks, you got to the correct answer. Now that certain number of clock ticks you can think of as an existential quantifier. It says there exists a number of ticks that if you execute this you get the right answer. But I have to give that number constructively. And it's a function of the input, and I actually construct the number of ticks it takes to compute factorial of n. And when we do compiler proofs, we typically relate those high-level clock ticks to low-level clock ticks. And so one of the reasons our proofs are liked by engineers is that they end up characterizing the number of cycles some high-level operation takes when they try to prove these correspondences. That one tick of this procedure invocation at the high level takes, k times x plus 6 instructions at the low level. And they like having these detailed maps between the so-called clocks of the two systems. But it's very complicated. And
because you have shown the proof of factorial, does it mean that the compiler is correct for the factorial?
Yes. You see, in the case of factorial, I didn't... I used the compiler to generate the bytecode, but I verified the bytecode. I didn't verify the Java compiler. I verified the bytecode that the Java compiler created. And actually that's important because the Java virtual machine, which we model, doesn't actually assume that the bytecode it's running was generated by the Sun bytecode compiler. It just gets bytecode off the web when it downloads something. And it's important that you be able to verify code at the bytecode level. So yes, I didn't verify the compiler, just that run of it, just the bytecode it produced.
Any further questions? In the case where the user wants to prove something false and the proof fails, what are the mechanisms to trace back the...
Not very good. I think I showed you. Let me go back to the ACL2 world, and let's try and prove again that fast sort of X is a perm of X. At the end, it printed 2 of 5 checkpoints, and one of them is that 1 is a member of X. It needed to prove that in order for this to be a theorem. So I would need a way to generate a counterexample to that. If I could generate a counterexample to that, say the list nil, then I could try to see whether that was a counterexample to the original. And it might be. It might not be, simply because ACL2 also, between the input and this point, it might have generalized and tried to prove something more general than the user asked, because that's so necessary in induction. And so you have to find a way to move your counterexamples past generalizations and through inductions in order to build a counterexample for the input conjecture. And so those are the 2 problems to think about. Is 3 problems. How do you generate a counterexample to a call of a recursive function like this? Then how do you move past generalizations, and how do you go through inductions?
Great. So I suggest, in the interest of time, that we will be here in the afternoon. Refreshments are actually up here, and also there is an outlook tomorrow if anyone would like to.
Right.
So and let's. So yeah, the refreshments are upstairs. So let's thank Jay for the phone call.
Thank you.